Okay, this is section 6.4, properties and some laws of vectors on page 302 of the textbook. Just a little bit more work with operations of vectors and discussing as they come up some properties and some special laws of vectors. So first up, we'll see the commutative property, and the commutative property basically states that it doesn't matter what order you add vectors in. The zero law, law for addition of vectors, if you add the zero vector to a vector, it remains the same. The vector it doesn't change at all. The zero property, vector plus the reverse of the vector, the negative of the vector, results in the zero vector. Associative property, again, is sort of an addition vector. Doesn't matter what order we add three vectors in. The first two could be added together to the third one, or we could take the second and the third one, add those together first, and then add the first one. The Scalar Multiplication Law, we talked about multiplication of vectors earlier. I can highlight or focus on the scalar, either multiply it by the vector and find the magnitude, or find the magnitude of the vector and multiply it by the scalar quantity after that. And the distributive property for vectors, similar to the distributive property for polynomials, we can apply the constant into the sum of the two vectors, or we could apply the constant into the individual vectors and then add together the resulting vectors. One other thing you guys may notice is the videos are going to look a little bit different now. I'm going to use Microsoft Whiteboarding and copy sort of slide by slide from Smart Notebook into whiteboard screens, and you'll see a different look and feel here. There'll be periodic breaks throughout the video, and that's fine. I'll just give you guys a chance to pause it and get around to doing some of these examples and seeing these examples. And the reason for this is I was just growing more frustrated. It seems like every video, the quality of my writing and the toolbox in Smart Notebook just wasn't the same as Microsoft Whiteboard. So I want to change this up and try this and see sort of see how this goes. Okay, so let's do the first one here. The two vectors A, 2i minus 3j. So A is represented by a combination of unit vectors 2i minus 3j, and B is another vector represented by unit vectors I and j. So I'm asked to find I and j in terms of A and B. So just a bit of a reverse, a little bit of work here. So this is going to involve very similar to systems of equations. So if I've got A, okay, and I've got B, okay, I can eliminate the I constant on the right hand side of my equation or my system by multiplying the second one, the second vector B, okay, by the factor of 2 and subtracting. Okay. So I'm just going to try and get a sharper feel. Okay, as I talked about this. Okay, so I'm going to keep A, but I'm going to multiply 2, the constant 2, by vector B, so I'm going to have 2i plus 2j, and then I'm going to subtract my vectors. So on the left hand side I've got A minus 2b. My 2i's are going to eliminate, and it's going to leave me with negative 5j. Okay, now I think I can solve for j on this side. If I divide my left hand side, both sides, by negative 5, I'm going to be left with j, and that's what I wanted. I wanted j in terms of A and B. Okay, now I'm just going to clean this up a little bit, okay, and write it as a scalar constant A, and then it would be a plus 2 over 5b, and that's vector j. Now I could further take out a factor of, okay, get rid of this negative. Often I don't write vector expressions with negative leading coefficients, so I could factor out, okay, a 1/5. I'd be left with negative A, okay, plus 2b, and if I wanted wanted to further clean that up a little bit. Okay, again, I'm just really being picky here, but I could. You may see a variety of different answers written like this. Okay, we're only half done though. I have to solve, I have to do the same for I. So in this case, I have to eliminate j. Let's look back to my original vectors here. How can I eliminate j? Well, I could multiply my vector b expression, right? I could multiply this second vector expression by 3 and then add my components, and I think that would eliminate my j. Let's try that. Okay, I'm just going to do that over on the side here. A equals 2i minus 3j. And what did I say? 3b. That would be 3i. And I can do that. That's a property, right? I've talked about this. I can multiply my vectors by scalar constants. Now let's add a plus 3b on the right-hand side. That would be 5i and 0. I didn't do this the last time, okay, but I'm going to do it this time. So the 0j is what happens here when I add the negative 3j plus 3j is 0j. And effectively, I'm just going to, I'm not going to really include that. So what have I got here? A plus 3b equals 5i. There I have I in terms of, well, I almost have I, plain old I in terms of a and b. If I divide by 5, now I have I in terms of a and b, and I'm just going to write that similar to the way I did the last one. That's I, and I'm going to factor out. Okay. There's my K2 expressions, I and j in terms of a and b. Okay, let's move along here. Okay, geometric proofs are commonly proven using vectors, and this is one application of vectors. Is actually, I think, quite a bit of fun here. So some of these, if you ever did earlier math classes in geometry, and you had a couple of properties or characteristics of certain shapes, there are reasons why this is the case, and they can be proven with vector proofs. So let's do this first one here. We've got a triangle ABC, and M is a midpoint of the vector AC, and N is the midpoint of vector BC. So I've got this new vector Mn, and it happens to have the property that it's a 1/2 of AB. Now that makes some sense, I think, if there were two midpoints that were used and created that happen to create Mn. It should make some sense, maybe, that if you can visualize this, that the length of Mn is the same as, okay, is 1/2 of AB. So let's prove this and see if we can do this. Now I find that the easiest and the best way to prove some of our work with vectors is just to start, okay, the proof, okay, with a vector string. Okay, so let's take a look at Mn, and let's say Mn is equal to Ma. So let's start at M and go to A, and then we're going to add AB. We're along this path, and then we're going to add Bn. And we've done this a couple of times before, where our vector Mn, okay, I start at M and I end at N, and I'm linking my point A and my point B here. So I'm kind of there, not quite there yet. I've started with what I wanted to prove, and I've introduced AB. So my job now is just to keep working on this and use some of the other properties that are given in the question in order to see if I can work this down. It might take me 4 or 5 lines to do this, and that's how I'm going to start here in a second. But I want to make sure that you guys know that there are a variety of different proofs you can do. Mn, the vector Mn, is a good starting point here, but it certainly doesn't have to start with what I've said, Ma plus AB plus Bn as a string of vectors. We can go in different order in a different way. Okay, so Ma, let's deal with Ma. Well, Ma, okay, Ma is 1/2 of Ca, right, because of the midpoint feature. I'm going to leave AB in here because it's part of my final answer here, and I'm going to talk about Bn. Okay, Bn Okay, so I'm going in an incorrect direction here. Okay, so I'm going to do a couple of things here with Bn and replace Bn, okay, with negative 1/2 CB. Okay, so CB was the vector that I was given, CB, and a half of CB. Okay, reversed. Okay, so half and then taking a negative of it is actually my Bn vector. Okay, so let's bring this together here. Let's bring our CA vector and our negative 1/2 CB vector. And I've got AB. Okay, that's fine. Now, I did that, okay, for a bit of a reason here. I'm going to, okay, switch, make this a half, and switch. Okay, maybe you can see what I'm trying to do here. Now I can factor out a negative 1/2, and I'm left with the string AC plus CB. Okay. So now what happens? AC plus CB, I can replace that with AB. Okay. And what do I have here? Negative 1/2 AB plus AB is equal to 1/2 AB. And my left-hand side was MN. Okay. Here, I promised you guys better penmanship, so I should start trying to do that here. So I've got, okay, MN, okay, is equal to 1/2 AB, and that's exactly what I was asked to prove here. Okay, so just do this carefully. Understand that it does take some practice to develop, okay, geometric proofs using vectors, but they are kind of fun, and just keep that vector path here as we move along. All right, next up is another geometric proof. Consider a polygon ABCD and let PQR and S be the midpoints of the respective sides AB, BC, CD, and DA. It's all shown on the diagram here. Okay, so we've got okay, some midpoints here. So this is a midpoint, this is a midpoint, this is a midpoint, okay, and this is a midpoint here. And I have to prove that the inscribed quadrilateral is in fact a parallelogram. So it's the midpoint sort of principle of any type of polygon that creates a parallelogram. The proof for a parallelogram, okay, is the following. Okay. Okay. And so PQ is the same as SR. Okay. And I've got to do the opposite sides too. So I would say something like SP is the same as. Okay, so not only magnitude but direction as well here too. Okay. So we start with a string of vectors. Okay. So let's full do the great big one here. So let's go PQ plus QR plus RS, okay, plus SP, okay, gets us right back to the beginning, the zero vector. Okay, so what else have we got here? PQ, okay, it has, now there's my PQ and there's my SR, so I really want to focus on, okay, maybe eliminating, okay, some of these other terms in here and switching that one around here. So let's look at QR. Well, QR, the vector QR, okay, is made up of, okay, a QC plus CR. Okay. I'm going to keep my RS in here. Okay. I'm going to put brackets around that. And SP, okay, is the vector SA plus AP. And it's still 0. Alright, now what? PQ, okay, Q, okay, so QC, okay, is really just half of BC, and CR is really just a half, okay, of CD, still going to leave my RS. And I'm going to do the same for this next one. So what am I at? SA. SA is a half of DA. And AP is a half of AB. And that's still 0. Okay, so I'm going to bring these together. Just rearrange some things here. Okay, so let's go plus CD. Okay, and now I can bring in the DA. And I can bring in the AB. That's the 0 vector. Okay, now I can factor out half and be left with okay. Now that string of vectors inside the parentheses BC plus CD plus DA plus AB is in fact the 0 vector. Okay. So I really have boiled it down to PQ plus RS is equal to 0, or if I like, okay, and that's the same as the vector SRF. So if I reverse the components, the tail to head, and get rid of the negative sign, it really is a negative, okay, and then negative here, but effectively it's SR. Okay, so if the vectors are the same, the magnitudes are the same. Good, and we've proven at least the part of it here. Now, similarly, okay, the other proof, the SP and QR goes the same way here. Okay, so remember the other one, it would start with, okay, now this is the second proof here. This is SP equals RQ here. So let me just try and establish my orientation. Okay, so that was proving the second part. That's QR is equal to SP. So we're going to start with the string again. Okay, this whole string, this PQ plus QR plus RS plus SP. It's done exactly the same way, except our focus is going to be on the other two pieces that we didn't touch here. And we're going to leave in QR this time. We didn't touch RS the last time, so we're going to focus on that. And I'm going to replace RS with RD plus DS. And I'm going to leave my SP and say that's 0. Okay, I'm going to pause this and continue with the solution. You guys probably could pick it up as well too, but we'll get back to it in a minute. Okay, pick up the rest of the solution. I did have to make a change. I should have proved originally it was QR. The magnitude of QR is equal to the magnitude of PS. Okay, so I've made those changes all through the proof of this, and I get my final statement that QR is the same as SP. Okay, and that's what I should have did originally. Okay, so that works pretty much the same as that first one, and that's a pretty intense one. I show you guys that as just sort of as an optional idea here, that we can use vectors to prove geometric proofs, and certainly practice a couple of those with homework and just have some fun with it and sort of see how that goes. Okay, next question coming up in one. Okay, next example is pretty simple simplification question. Simplify the following expression. So we've got 6a plus 3b, I'm just going to say that equals plus 3c minus a minus 3b, and this is sort of a combination of the distributive property. I'm going to collect like terms. I caution you that if you don't do this line, just be very, very careful with any potential mistakes that you might make. Never hurts to do it, to collect like terms so we can line them up. I've still got my 1, 2, 3, 4, 5, 6 terms, 1, 2, 3, 4, 5, 6. So now I've got 5a plus 0b. Again, doesn't necessarily need to be included. Okay. Okay. And if you like, we could factor out. Okay, that's it for that one. Okay, pretty straightforward, very, very straightforward, I think. Okay, and we'll get into the next and last example here. Okay, the next one is another simplification step. We're given x in terms of a string of vectors, y in terms of a string of vectors, and z in terms of a string of vectors. Okay, I'm just going to highlight those by way of, okay, the comma here. And I want to determine each of the expressions, so x plus y. So x plus y is simply just going to be 3i minus 4j plus k, and then y is a plus j minus 5k. So I can bring my components together. I don't have any i's, just a 3i minus 4 plus j is minus 3j, and then a plus k minus 5k is minus 4k, and that's it. Okay, the only problem here might just be the confusing nature of this question. There's lots of terms and different things here, but vectors, treat vectors just like terms, okay? Just like terms. So in this case, x minus y is going to be the same start, except it's going to be a minus. Okay, so I need an extra line in here, 3i minus 4j plus k minus j plus 5k. That way I preserve the subtraction property of it. This will be 2i. Oh, no, my mistake. There's no I term. Okay, so it's 3i. There's no I term in the second vector. Minus 5j, and then a plus 6k. Okay, the next one's a little bit more challenging. Okay, I've got an x minus 2y plus 3z. Okay, so I've got 3i minus 4j plus k minus 2, and the 2y happen to be j minus 5k, and then a plus 3z, and z, I don't know that one, minus I minus j plus 4k, so minus I minus j plus 4k, and I think I wrote that down right properly, but I'm going to double check. I don't want to make that mistake. Okay, so I've got, not hard, just a little tedious, and the potential for a lot of errors. Okay, if you're not paying attention and trying to do too much, the potential for a lot of errors goes down here. Now I'm going to collect my like terms. I've got 3i minus 3i, okay, and I don't have any more I terms, so I'm just going to, my j terms, minus 4j, minus 2j, and a minus 3j, bang, 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 and then now I've got a k plus 10k plus 12k, okay, and bang, I'm just going to do a count in my original 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, good, now I can bring them together. 0 I, okay, minus 9j plus 23, I think, 23, 10, 12, 22, 23, k. Now I don't normally write, okay, so I would write minus 9j plus 23k. Now again, as an aside, that I, j, k are actually unit vectors, so we could write that as component vector components. Okay, that is it. That's a lot, but I don't think anything is too challenging in here. Have some fun with the geometric proofs if they're assigned in homework questions, okay, and just work through carefully the operations and sort of the combinations of vectors. Good luck, have fun, bye.